Good morning, everyone. Welcome back to this second day of the school for the second week. We will continue today with Cristina Garcia Vergara talking about large-scale structure of the universe. Cristina, thank you very much. Good morning, good afternoon for you, and the space is yours.
Okay, gracias. Thank you, Esteban. Sorry. And today we will continue with the course of large-scale structure of the universe. And today I'm gonna focus more on the measurement of the large-scale structure. How can we measure clustering? And then today the class will be a little bit more technical, but I hope that you can follow this well. I'm gonna share my screen. Here we go. Okay, then I'm gonna start with repeating a little bit some of the things that we discussed yesterday, just for you to get familiar with the topic again. This is most like a summary of what we talked yesterday. This is a schematic view of the structure formation and evolution in the universe. You can see redshift in the x-axis, and that is basically time. We started with an explosion, the Big Bang. Then we had an inflation phase in which the space grew up super fast. And we can have an observational proof of the state of the universe just after the inflation, which is called CMB. In the CMB, we can already distinguish some matter overdensities and matter underdensities. I explained to you that the universe at large scales is pretty homogeneous, but we have a lot of inhomogeneities at small scales. Then I explained you how those inhomogeneities grow over time. Basically, massive overdensities become more massive on time, and underdensities become less massive on time, which is what I show using this Millennium simulation that I'm showing here. This is just the dark matter distribution. Then I explained you that at some point, a matter overdensities start collapsing to form dark matter halos. And inside of dark matter halos, galaxies can be formed. And normally we have at least one central galaxy in a dark matter halos, but we also can have satellite galaxies in the same dark matter halos. And the very common example of this are cluster of galaxies, which contain several galaxies and a large amount of dark matter. I also tried to motivate you to understand, to try to teach you why it's important to measure the large-scale structure. Yesterday, we just talked about qualitative aspects of the large-scale structure. We can distinguish the structure by eyes only, but we really need to quantify mathematically this, because the large-scale structure depends on cosmological parameters and on the physics of galaxy formation and evolution. Then if we can constrain and measure the large-scale structure mathematically, we can constrain cosmology and physical process of galaxy evolution and formation. Then that is why this is so important. Then today I'm gonna talk more about how can we measure this. I will start with a very simple explanation about what is clustering. Okay, so the second lecture starts here, basically. Just to define clustering, clustering is a quantity to quantify, sorry, there it's redundant, but to quantify how grouped the objects are in the space. Then in basic terms, the more grouped objects are, the stronger the clustering is. Then here, for example, I'm showing 3 different distribution of points. In our case, those points are galaxies, but clustering is applicable for anything, stars, galaxies, cluster, people, any type of data. Then in this first panel, we have randomly distributed points. Then basically, we can say that they are not clustered at all. In the second panel, I'm showing, and you can already see that we have a concentration of points here in the center. Then we can say that the objects are clustered, has a small cluster. And in this extreme case, the clustering is much more stronger. Then you can see that points are more accumulated at these small scales. Then we can say that this is a strongly clustered population. This is like the very basic idea of what is clustering. But we need also a mathematical formalism to describe the level of clustering, then how much strong this clustering is compared with this one or compared with this one. And that mathematical formalist is the 2-point correlation function. I already introduced it a little bit yesterday, but I will repeat this now. The typical definition for the 2-point correlation function is this measure excess of probability, dp, over a random occurrence of finding a galaxy in a volume element dv at a separation r from another galaxy. That is the formal description of the 2-point correlation function, and is encapsulated by this formula here. Then here, n is the mean number density of the galaxy sample in question, then the number density of galaxies in the universe, like the mean average over all the space. dV is the volume, and this is the correlation function. Then, for example, using the same example as in the previous slide, this is a random distribution. Then we don't have clustering. That means that the correlation function is 0, and then this equation becomes to this form here. Then the number of objects that we will find is basically defined by the number density, the average number density of objects in the universe, right? It's just, that means that if you find a galaxy in the sky, you don't know about the probability of finding another galaxy close to that one. Those probabilities are completely independent, and the position of the galaxies are not correlated at all. In the other hand, if you have a more clustered population, then the 2-point correlation function is not 0, but has a positive value. And then you recover this expression here, which is basically this case, but with this term 1 plus c. In this case, this means that if you find a galaxy in the sky, then is very likely to find another galaxy very close to it. That means that when you have a positive clustering, that means that the probability to find a galaxy close to another is higher in comparison with this random case, okay? And one important thing is that the 2-point correlation function traces the amplitude of the clustering as a function of physical scale. Then clustering depends on the scale. We can have like a population with very strong clustering at small scale and very weak clustering at large scales. And with scales, we mean physical scale. Then, for example, if a population has a strong clustering at small scale, then if I pick one galaxy in the sky, I have a very high probability to find another galaxy very close to it. But if the clustering is weak at large scale, then the probability to find a galaxy at long distances from the first one is not really very high. Then this is a dependency of scale. Then some people, well, a lot of people actually have been doing some observations of the two-point correlation function using different samples of galaxies, mostly in optical wavelengths. And the results so far suggest that the two-point correlation function is well described by a power law, as I'm showing here with this equation. Normally, you have two parameters here. R naught is called correlation length, and gamma is the slope of the correlation function. Then basically, the function here indicates that we normally have strong clustering at small scales and weak clustering at large scales. That is what happened in the universe for basically all type of populations in the universe, like galaxies, quasars, different type of galaxies. Then all of them have this power law shape. And normally the slope don't variate so much. Typically it's found to have a value around 1.8 with small variations only. Then to show you more how is the effect of different correlation length or different slope for this function, I'm showing here the plot of the correlation function as a function of the distance, the distance between 2 points. And if you have a higher correlation length, you basically have a higher amplitude in the clustering. Then basically this moves this plot like up or down. And the effect of the slope is basically that one, you're changing the slope. Then if you have a population with a steeper slope, you will have with higher value of gamma, you will have a steeper slope as I'm showing here. Then in general terms, higher clustering implies a higher two-point correlation function and then a higher correlation length, or R naught, which is the correlation length is parameterized with this R naught value. Okay, then how can we measure the two-point correlation function? Given that the correlation function is a measurement of how grouped are the galaxies compared with a random distribution, that is exactly the way in which we can measure it. Then specifically, you have to count pairs of galaxies as a function of separation and divide that by what is expected for an unclustered distribution, which means a random distribution of points. And then to compute the clustering, we need to construct a so-called random catalog, which is basically a catalog that follows the same geometry of your data, but the objects in this catalog are randomly distributed on space. This random catalog need to be large enough in order to decrease the Poisson errors that you can have when you estimate when you count the pairs with this catalog. Then several estimators have been suggested to measure the correlation function. Then this is the more basic one. Then DD here is the code data. This is just the number of pairs of galaxies in beams of separation. RR is the random, which is the number of pairs of random points in beams of separation. Then it's the same as the data, but using the random catalog that you created. And ND and R here are just the number density of galaxies in each one of the catalog. Then you basically have to normalize these quantities to have a fair comparison. Then I will show you how this really works in practice. Then imagine that you have a distribution of sources of galaxies in the sky, like this one here. This is the data that you have. Then the first step is that you have to create a random catalog, then follow exactly the same geometry here, the same coordinates, and you just simulate sources, positions within this area, and you randomly distribute those points over the area. If the data has an empty spot here because any problem of the image, or sometimes we have like bright stars that are contaminating the flags, and we cannot actually see very well the information here. We normally mask that region. And if that is the case, your random catalog also have to follow exactly the same geometry, then you cannot simulate galaxies in this area here. Yes. Then to compute the data, you basically have to take one galaxy of your catalog, which is represented as the blue galaxy here, and you have to count how many galaxies you have at different distances from that galaxies. Then you define a binning here. This is the distance in megaparsecs in this case. Then you have between 1 and 10, between 10 and 20, etc. Then you focus on this galaxy and count how many galaxies you have at the different separations, and you have to store that number in this array. Then when you finish one galaxy, then you pick another galaxy of the same catalog and repeat the same thing using the same binning. Then when you finish doing this with all the galaxies in your data catalog, then your DD array will look like this one. Then, for example, you have 63 galaxies at distance between 1 and 10, 63 pair of galaxies. Then that is more or less the idea. Then you have to repeat the same procedure for the random catalog. Exactly the same thing by using the simulated sources that you have. And then you basically have to divide those quantities to compute the correlation function as using this formula, for example. And that's it. Then other estimations has been proposed also. Here I'm showing the more important ones. This is the natural estimator, the Davis and Pibus, the Hamilton, and the Langley and Shalai estimator. All of them are analogous. Basically, those will give you the same answer, the same measurement of the correlation function, but the differences are more focused on some of the estimator are better to handle, for example, edge effect, like because your images normally are not like circular. You have square images, and then this is the edge. And you also have edge because this kind of behavior in your image, then you have to, some estimator, in particular this one, the Langley-Shalai estimator, can handle better the behavior of the number counts in the edge. Also, they have different uncertainties and different statistical properties, but in general, all of them should give you the same answer. And normally this one, the Langley-Shalai, is the preferred estimator, is the most used estimator because it's considered that it gives you the less uncertainties, as is less sensitive to the size of the random catalog, for example, then this is normally more used. You can also realize that some of the estimator has also the term DR here, which is basically the same idea, but to compute DR, you have to use your data catalog with your random catalog and count pairs between those two catalogs. But the idea is basically the same. Then the Langley-Shalai estimator is using also this DR term.
Excuse me, Christina, you have a question in the chat?
Yes, please.
Is NR expected always to be much greater than ND?
Yeah, good question. Yes, we need to simulate the random catalog. Then that means that we can choose any size that we would like. And normally you need to use a very large size because that decreases the Poisson errors. And then normally you have to use, I don't know, 10,000 or more random points. There are some definitions that people normally use, and some people suggest that a good number for the random catalog is to be 20 times larger than your data catalog. That you normally have to have a much larger random catalog compared with your data. Okay. So in the practice, I will show here how can you measure this considering the data that you have. Because of course, ideally we will need the 3D information for the sources in your survey. That means the coordinated right ascension and declination, but also the redshift. But that is not always the case. We usually have only 2D positions because getting the redshift of their sources is really hard and expensive in terms of telescope time. Then normally we only have the 2D information. But even in that case, we can anyway measure the clustering of the sample. Then I will talk about two different correlation functions that are used normally in astronomy. And you can use one or another depending on what type of data you have. Then, for example, when you have the 3D data, then you have redshift information of the sources. You basically can know what is the spatial distribution of the sources in the sky. Then you can measure the projected correlation function. But if you only have 2D information available, then you basically just are seeing the sky and you don't have information about how far the source is. Then you only can measure the projected angular correlation function. Then those are the two main or typical correlation function that you can find in papers, in astronomical papers. Then I am going to talk first about the projected angular correlation function. As I said, this is the reality, but when you don't have redshift, you basically are seeing all the galaxies collapsed over redshift space, and you only see the sky positions. Then you have something like this that I'm showing here. The definition for the angular correlation function is exactly the same one as the 3D correlation function, but here you have omega theta, which is the angular correlation function, and instead of the volume, you have only solid angle, because you don't have information about how much volume you are tracing. You don't know if you're tracing from redshift 1 and redshift 3 or from redshift 0 and redshift 10. You don't have really that information because you don't have the distance from the sources. And this correlation function also has a power law shape represented by this equation here, but in this case, we don't have the R0 and gamma parameters, but instead of that, you have A and beta parameters, which in this case, A is the amplitude of the clustering, like similar to R0, and beta is the slope. But those are not the same as R0 and gamma. Then you have to make a procedure to convert those parameters to the real space parameters. And to do that, you need to know the redshift distribution of the sources that you are working with, which is actually something that is not very well known normally. And if you don't have redshift information of the sample, you don't really know if the redshift distribution is peaking at redshift 2, redshift 1, or if this has a Gaussian shape, or if this is flat. You normally don't have that information, and you have to use other sources of information, for example, simulations or something like that. But you need to assume a redshift distribution to convert from the angular correlation function to the 3D real space correlation function. And to make this conversion, you normally use what is called the Limber equation, in which you can relate the angular with the 3D correlation function by integrating over the line of sight, because that is actually what we are seeing. We are seeing the distribution of galaxies integrated over the long line of sight. Then with that equation, you can relate then the parameter A, which is what you measure directly from your data, with the parameter R naught and gamma using this equation. This here, the N to the S, is basically the redshift distribution that you have to assume for doing that. And G is a term in which depends on cosmology. Then you have to assume a cosmological model, but normally that is not like a big problem because we more or less know well the cosmological parameters. And the slope beta is related with the slope gamma in this very simple way. Then I'm trying to give you a cookbook for you to be able to measure the clustering of a population. Then we actually will work on this in the workshop in the afternoon. Then you have first your data here. You measure the data term. In this case, you only can measure angular distances. Then that is why I call this theta, and is in arcsecs or in degrees or any other angular unit. And it's exactly the same procedure, but you just count in circles, in projected circles. Then only you can compute the angular distances. You repeat the same for your random catalog. And in this case, your random catalog just need to follow the 2D position or 2D geometry of the survey that you have. Then you use an estimator to compute omega theta. And again, you can use any of the estimator that I showed before. Before I said that is an estimator for the 3D for the real space correlation function, but those estimators also work for the angular correlation function. And then you can fit the measurement that you have to obtain the parameters A and beta. Then you assume a redshift distribution and use the Limber equation that I showed before to obtain R naught and gamma, which is our goal. Basically, when you measure clustering, the goal is to obtain the parameters R naught and gamma, because those are the informative parameters. Then two important things about the angular correlation function. One is that the parameter A can be dominated by errors given the lack of knowledge of the redshift distribution of the sample, which is what I told you before. We normally don't know how is the redshift distribution. And the other point, which is very important, is that we are collapsing the information over very large volumes. And that means that the signal can be diluted, which is called projection effects over the line of sight. Then, for example, if you have a population which is strongly clustered, intrinsically strongly clustered, but you only have 2D position of the sources, then you are integrating over a very large line of sight over all the redshift space, and then you could observe this as a very weak signal, just because you are averaging over the entire space. Then that is one problem of the angular correlation function, because sometimes even if the population is strongly clustered, you're gonna measure a weak signal. Then normally to mitigate a little bit this effect, if you have, for example, a little bit of information of redshift, which we call normally photometric redshift, those are redshift that are not so precise, but are more or less precise, you can just split the sample and just focus on certain redshift window. Then you avoid to dilute this signal over a very long line of sight. Here I'm showing just an example of the angular correlation function measured for galaxies from Sloan in 2002 by Connolly et al. You can see that you have, normally we always use logarithmically spaced bins here. That is because this allows us to trace better the small scales in which the clustering signal is expected to be much stronger than large scales here. Then that is why normally people may use logarithmically spaced bins. Okay, then now we also have the projected correlation function. Then in the very nice case in which you have the redshift of the sources, you can measure this kind of correlation function. And we are going to see that even if you have the redshift information of the sources, we are not actually able to measure the real distance r between the sources. I'm going to explain this better. First, let me show you a little bit the geometry of the problem here. Here you have one object, one galaxy, for example, and here you have another one. The 3D distance between them is this small r. This here is the plane of the sky. Then basically the right ascension and declination give you the position of the sources in the sky. And this axis here is the redshift, basically the line of sight. Then if you have the redshift of both objects, you can compute the redshift distance between them, which is called p. But this is the distance. You always, when you have redshift, you always can translate redshift to distance using cosmology, right? The redshift basically indicate the distance which the object is. Then if you compute the distance to the object number 2 and to the object number 1, you can compute the difference between that, and that is called p. This is normally computed in physical units, megaparsec, kiloparsec, or something like that. And also you can define the distance between the two objects projected in the sky plane, which is called r. This r, big R, is basically the same as theta that we measure for the angular correlation function, but in this case, given that we have redshift information, we can measure theta not in arcsecond, but we can convert this distance in physical distance using the redshift at which the source is. Then basically here r, big R, is in units, in physics units, megaparsec or kiloparsec. Then we have much more information than in the other case. Then just for simple geometry, you can see that the 3D real distance between the two objects can be written by separating the two components, the parallel component to the line of sight and the perpendicular component to the line of sight. Okay, then as I said, even if you have the redshift of the sources, you cannot really measure this 3D distance because the redshift is an indicator of the distance, but it's not very precise. Then I'm going to explain this here. When you measure the redshift of the source, you are basically measuring the velocity at which the source is going farther away from us, right? And using cosmology, you know that objects at larger distance will have a larger velocity, right? However, you also can have galaxies having peculiar velocities because they are interacting with other galaxies close to them. Then a very known example of that is galaxy cluster, for example. In a galaxy cluster, you have a lot of galaxies at the same distance from us. However, the galaxies are orbiting and have random velocities between to one to the other. And then if you measure redshift, you will have a very different redshift for two different galaxies in the same cluster, even when they are at the same distance from us. Then in that case, we are talking about redshift space distortions, because in that case, the redshift is not a very good indicator of distance and will be a little bit impacted by the peculiar velocity of a galaxy in the space. Then, for example, here, this is a simulation of this effect. This is the 2-point correlation function in the case that all the particles are not interacting or don't have velocities compared with the other particles. Then you will measure a perfect 2-point correlation function, and you have this circular. Those are the contours of the correlation function. But in this case here, for example, if you include the velocities that particles have within matter over density, then you're going to see that this correlation function will be elongated over the line of sight. And similarly, because you have also particles going in the other direction, you also can have that the correlation function is elongated in the sky plane. Then when you combine those two effects, you get this one, and you're instead of measure this correlation function, which is the real one and not distorted, you're gonna measure this one. Then actually, this is a real measurement of the sources in the 2DF data of the galaxies, and that is actually what we can measure for the correlation function. Then this effect is real and is measurable in your correlation function and is impacting this for your measurement. Then that is the reason why we don't have actually knowledge of the exact distance between the sources. Then to solve this problem, what we have to do is just to write the correlation function in 3 dimensions as a 2-dimensional 2-point correlation function. Then basically we write C in terms of R, the projected distance between points, and P, which is the distance along the line of sight. Then this 3D correlation function, if you integrate this over the line of sight, you can obtain the projected correlation function. Then this is the definition of the projected correlation function. What you are doing exactly is that you pick one galaxy in the space, and you are just counting pairs in a small redshift range from it. Then if you have a very close pair in the sky, but it's a very long distance in redshift, you are not counting this, as in the case of angular correlation function. Then here, if you assume the typical power law for the correlation function, then you can write this in these two components. You put this here in the integral, and you can actually solve the integral analytically, and this is the solution. Then this show you how the projected correlation function is related with the parameters R naught and gamma, which are the parameters that we are interested in. Then when you have 3D information, you can directly to measure R naught and gamma, actually. In this case, you are not assuming a redshift distribution as in the angular case, and you just can plot your measurements here, fit a power law, and you are gonna obtain the R naught and gamma parameters. Then in the practice, you don't have to integrate this until infinity here, because at some point, at some redshift distance from the galaxy will not be more strongly clustered anymore, then the signal will be very weak. Then in the practice, you normally use a value here for the redshift, for the distance in redshift space to make the integration. Then I'm going to show you this in a bit. Then the cuckoo. Yeah, sorry.
You have a question. Sorry to interrupt. You have a question here in the chat. What is the percentage uncertainty, more or less, between the real C and the distorted C due to peculiar motion?
Well, that is, you can see here, for example, this is the perfect case, and this is what you are observing. Then here you have around 10 megaparsec over H. Then in some cases, the distortion can be pretty long. It's hard to say in advance because it depends on, for example, if the galaxies are in a cluster of galaxies, you will have more stronger peculiar movement, and then the distortion will be more important. But if you don't have so massive structures, then this distortion can be smaller. Then how much variation depends on in how massive the structures are for the particular sample that you are measuring your clustering. And I hope that answered the question. Okay. So this is the cookbook that I prepared for you. In the case that you have a survey with 3D positions, you are not creating DD as a one-dimensional array anymore, but you have a two-dimensional array. You have beams in R, which is the distance, the projected distance in the sky, and you have also beams in P, which is the distance in redshift space. Then it's exactly the same procedure. You count pairs at the different distances, and you're filling this array. Here you have physical units for both components. That is the nice part that we cannot make with the angular correlation function. And as I explained before, you only normally go up to a certain maximum redshift distance, because if you continue here to longer distance, you're going to have a very small number of pairs because you are too far from the galaxies, and given that the clustering decrease with the distance, you expect to have a weak signal here. Then you're basically not normally stop at some point. You, in this case, also have to create a random catalog, but you have to include you have to mimic basically the geometry of your survey in both dimensions, then in the sky, but also in redshift. But that is not a problem because you have the redshift information of your sources, then you can create random catalog following the same redshift distribution. But you have to consider it. Then you can use any of the estimator that I showed before to compute the two-point correlation function. Then this two-point correlation function will also be a grid like this one. Then you can integrate the values of the grid over the p direction to obtain omega r. Then you can feed the measurement omega r, and you will get directly the parameters r naught and gamma. Then this measurement is much more direct to obtain the parameters, and you are not assuming any redshift distribution, you're not assuming any cosmological parameters. This is just the measured quantity from observations. Then the same as before, here I am showing an example of a projected correlation function, also for galaxies in the Sloan's Digital Sky Survey, measured in 2011 by Sehavi et al. In this case, they separate in different luminosities the sample, but basically I just want to show you how those kind of plots looks like. Then this is a power law shape. You have different amplitudes, more or less very similar slopes. We will talk in more detail about this measurement tomorrow in particular, but like to interpret what does mean. But for now, I just wanted to show you how this looks like. Okay, then just to summarize what we have talked so far, we have two cases normally in astronomy to measure the correlation function. If we have only 2D position of the sources in the sky, which is the more common situation, we can measure the angular correlation function. Then we have to fit this measurement, which give us the parameters A and B that are our observable quantities. Then you have to assume a redshift distribution and cosmology, and you can get the parameters R0 and gamma. In the case that you have 3D positions in the sky, then a survey with redshift information, you can measure the projected correlation function, in which case you are integrating over a very small redshift range. And then you feed your measurement and you get directly the R0 gamma without any other assumption. Then another important thing here is that, as I mentioned, for the angular correlation function, you have projection effects in which you can dilute your signal because you are integrating over large volumes in the universe. But in the case of the projected correlation function, that is not happening because you are actually computing the pairs in a small volume because you choose this redshift distance to be small, like as I said before, around 100 megaparsec over H. Then you don't have dilution in this case. Then what you measure is exactly what it is. I mean, if your sample is strongly clustered, you will measure a strong clustering, which is not always the case in the angular correlation function. Okay, and I have the break here because I think I have been provided a lot of information and it's very technical. Then I don't want you to be so tired. Then we can stop here and come back in 15 minutes. And in the second part of the lecture, I'm gonna talk a little bit more about how can you estimate the errors in the measurements, which is very important for clustering measurements, and also give some other details. Then, yeah, we're 10 minutes ahead, but I think it's fine.
Okay, perfect. Thank you very much, Christina. Then, yes, we are a couple of minutes ahead. So let's say we reconvene and at 9:05, so 3:05 in your time, 9:05 Colombian time, and we will continue with the second part. So far, there are no more questions in the chat, but remember that all the questions can be passed to Christina in case you have them, and we can do it now or we can do it at the beginning of the second part of this lecture. Christina, thank you very much and see you in 15 minutes.
Yeah, thank you. See you.